Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idea Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to E-Lecture series on BSc Electronics Practicals. In this lecture, we are going to discuss about LCR parallel resonance circuit. In this LCR parallel resonance circuit, inductance, capacitance and resistance are connected in parallel combination. Then voltage across the capacitor is studied for various input frequencies. This circuit will act as a receptor circuit. This circuit will receive the input frequency. That is the speciality of this LCR circuit. We are going to practically do this LCR circuit. This lecture will be organized in the following way. First, aim of the experiment, then apparatus required to do this experiment, formula, theoretical formula used to calculate the resonant frequency, quality factor of the circuit, and bandwidth of this LCR circuit. Then observations. By varying the input frequency, keeping the capacitor, resistor and inductor value constant, will be finding the voltage across the capacitor for various input frequency observations. Then result analysis of this experiment. In this way, this lecture will be organized. Now let us go to the aim of this experiment. Aim of this experiment is to study the frequency response of a parallel resonance LCR circuit and determine its resonant frequency, impedance at resonance and quality factor and bandwidth. These are all the parameters to be determined in this experiment. Next, apparatus required to do this experiment. First, a function generator from which frequencies, input frequencies are obtained. Different input frequencies from 1 Hz to 10,000 kilohertz can be obtained. Then inductance coil. Here I am going to use a variable inductance box. Then capacitor. Here I am going to use a variable capacitance box, then a variable resistance box, then a multimeter to study the peak voltage, a peak to peak voltage across the capacitor. These are all the components required to do this experiment. Circuit formula used to calculate the theoretical value of the observed parameter. We will be observing the resonant frequency from a graph plotted between the input frequency and the voltage drop across the capacitor. By that graph will be like an inverted parabola. The maximum frequency at which the output voltage will be maximum is called resonant frequency, or the resonant frequency at which the output voltage is maximum is called resonant frequency. Then from that we can calculate the resonant frequency. We can compare the observed resonant frequency with the theoretical frequency by the formula F resonance is equal to 1 divided by 2 pi into square root of LC, where the inductance and capacitance of the circuit plays a prominent role in determining the resonant frequency of the circuit. By tuning or adjusting the values of inductance and capacitance, we can fix the desired particular resonant frequency. Then quality factor of the circuit is evaluated from the formula F naught divided by Fb minus Fa, where that F naught and Fb can be seen from this graph. Here a graph is drawn between the input frequency and the output current. We can convert the output voltage into output current. We can draw a graph between input frequency and output voltage. The frequency at which the output voltage is maximum is called F naught, that is resonant frequency. Then the frequency at which the output voltage start increasing, trying to reach the maximum value, is called lower cutoff frequency, and the frequency at which the output voltage starts decreasing is called upper cutoff frequency. By knowing the resonant frequency, lower cutoff frequency and higher cutoff frequency, we can calculate the quality factor of the circuit. Quality factor is equal to F naught, that is resonant frequency, divided by the bandwidth. Theoretical quality factor can be obtained by the formula Q is equal to XL by R, where XL is the reactive impedance and R is the resistance given to the circuit, which is equal to 2 pi F resistance into L divided by R, F resonance. 2 pi into F resonance into L divided by R gives the theoretical quality factor of the circuit. Then bandwidth of the circuit is equal to resonant frequency over quality factor. Theoretically, you can calculate the bandwidth. Then experimentally, bandwidth is obtained from the difference between the upper cutoff frequency and lower cutoff frequency. These are all the comparison between practical observation and theoretical calculations done using the formula. This is the next part of this experiment. Next, circuit diagram to be constructed to study this parallel LCR circuit. First, a voltage source is taken. Then from that voltage, here voltage source can be a 10 volt voltage source. Then a sine wave is obtained as output from this voltage source with varying frequencies. Then that is connected parallel to a resistance and an inductance and a capacitance. Voltage across the capacitance is studied is noted down for different input frequencies. This is the circuit diagram used to construct this experiment. Next, observations. You can keep the inductance, resistance and capacitance constant, vary the input frequency and note down the output voltage across the capacitor. So, for different input frequencies, note down, then plot a graph between the input frequency and the output voltage. The graph will be like this, ascending one and a descending one, that is an inverted parabola. The maximum frequency is F naught. Then from that maximum frequency, you can calculate the resonant frequency. This is the observed resonant frequency. You can compare this observed resonant frequency with the calculated resonant frequency. Then bandwidth can be calculated using the theoretical formula. Then quality factor of this circuit can be calculated. This is how you can initiate the experiment before getting into the laboratory. Now we will go to the experiment. This is the apparatus setup to do this LCR parallel resonance circuit. First, a function generator is used as input source. From this function generator, variable input frequencies can be obtained. Then output from the function generator is connected parallel to the resistance box. This is the resistance box. This resistance box consists of 4 dials. That means you can vary the resistance from 1 ohm to 10,000 ohm. So, such a variable resistance can be obtained from this resistance box. Then a parallel lead goes to the inductance box. In this inductance box, you can vary the value of 10 millihenry to 1000 millihenry. So, such a variable millihenry output can be obtained from this inductance box. This inductance box will store the energy in the form of magnetic energy. As you know, in the LCR circuit, oscillation is produced because of the transfer of energy from one component to other component. Resistance opposes the flow of electrons. Inductance will induce a magnetic field from the electrons coming to the inductance. Then capacitor will store the energy or charges coming towards it. So, like that 3 different electrical components are connected in parallel combination. When energy transfers from one component to other component, it changes its form, like magnetic energy, then charge, like that energy is changing its form. When the energy changes its form, oscillation is produced. Such oscillation comes out as a frequency. That is this LCR parallel resonance circuit. So, here in this inductance box, you can vary the inductance from 10 millihenry to 1000 millihenry. Then a capacitance box, decad condenser box. In this decad condenser box, you can vary the capacitance from 0.001 microfarad to 1 microfarad. Such a wide variation of capacitance can be obtained from this variable capacitor. You know, by adjusting the value of the capacitor, you can fix the resonant frequency of the circuit, you can vary the bandwidth of the circuit, you can fix the quality factor of the circuit. Then a multimeter which is fixed in AC mode. In that AC mode, you can measure the voltage across the capacitor. You can measure the voltage across the capacitor. So, these are all the components used to do this LCR parallel resonance circuit. Now, let us start our experiment. To start our experiment, I have fixed the cutoff frequency as 35,000 Hertz as the cutoff frequency or resonant frequency. 35,000 Hertz is the resonant frequency. To get this 35,000 resonant frequency, this resistance is kept as 100 ohm, then inductance is kept as 600 millihenry, then capacitance is kept as 0.2 microfarad. These are all the values I kept to get a resonant frequency of 30,000 Hertz. Now, so in this function generator, the output voltage is kept as 10 volt. Output from the function generator goes as input to this LCR parallel resonance circuit. Here I kept this as 10 volt, then sine wave is fixed here. Then this frequency selector is kept at 10K. So, when I rotate this, you can vary the frequency. So, now the frequency is at 10 kilohertz, then each line will be 1. So, 0.1 into 10 kilohertz. So, it will be 1 kilohertz. So, it will be 11 kilohertz, then 12 kilohertz, 13 kilohertz. Like that, we can vary the input frequency by simply rotating this one. As I told earlier, the resonant frequency for this circuit will be 35,000 Hertz or 35 kilohertz, 35 kilohertz, that is the resonant frequency. Before resonant frequency, how the output varies, we are going to see that. Then after resonant frequency, how the output varies. We are going to note down these values and we will see the plot across this. Now the resistance is kept as 100 ohm. So for this 100 ohm, the resonant frequency is 35 kilohertz. From the resistance, parallel connection comes to this inductance box. As I told earlier, we can vary the inductance values from 10 millihenry to 1000 millihenry. Here I kept the inductance value as 600 millihenry, which is an optimal inductance value to get the resonant frequency of 35,000 hertz. Next, from this inductance box, parallel connection goes to the capacitor. This is the decayed capacitance box. From the inductance box, connection comes to this capacitance box. In this capacitance, you can vary the values from 0.001 microfarad to 1 microfarad. Here, to get the resonant frequency of 35 kHz, I have fixed the capacitance value as 0.2 microfarad. So accordingly, you can fix your own resonant capacitance value to fix the resonant frequency. Then from this capacitance box, a parallel connection is given to this multimeter. Using this multimeter, you can measure various component values of the electronics, various component values. Here, we are going to measure the voltage drop across the capacitor, AC voltage drop across the capacitor. So you can see that measuring knob is kept in the AC voltage. AC voltage, it is there. Now, when I adjust the frequency, you can see the variation in the output voltage. Now, I am increasing the frequency from 10 kilohertz. You can see the variation in the output voltage. The variation is an increasing one. When we increase the frequency, you can see the increase in output voltage. As the frequency increases, output voltage increases. For 30 kilohertz, the output value is 0.49 volt. For 35 kilohertz, the output value is 0.50 volt. Then for 40 kilohertz, the output voltage is again 0.50 volt. Then for 45 kilohertz, the output voltage is 0.51. So here it starts to stagnate. After further increase in the input frequency, output voltage keeps same. Then it keeps same even for 50 kilohertz. Then as I increase further, it starts decreasing. So this is how you can find the resonant frequency of this circuit. So due to some practical error, the resonant frequency has shifted to the 40 kilohertz. But theoretically, if you calculate, the resonant frequency will be around 35 kilohertz. This kind of error is common in practicals because every component has some error. All those errors will accumulate in the result. So result will have some error. But the allowed error in a practicals is maximum 20%. Above 20% error occurs, then we have to repeat the experiment. So after noting down all the output voltage for various input frequencies, you can plot a graph between the output voltage and the input frequency. So the graph will be like this. In this graph, you can note down the maximum frequency. you can compare that maximum frequency with the theoretical one by substituting that in the formula F resonance is equal to 1 divided by 2 pi square root of LC. Here we kept the L value as 600 millihenry and capacitance value as 0.2 microfarad. So if you substitute that too, then it will come around 40,000 hertz. So that is the practical value. Now come and substitute that 40,000 hertz in the bandwidth calculation. So bandwidth calculation 40,000 hertz divided by the quality factor. So quality factor can be obtained from the graph as F naught divided by FB minus FA. So quality factor is obtained. That quality factor is substituted here. So here bandwidth will be between 30,000 hertz to 50,000 hertz. So the difference will be some 30,000 to 50,000 is 20,000 will be the difference. So 20,000 hertz frequency can be passed by this LCR circuit. Same concept is used in designing the low pass filter and high pass filter. Low pass filter and high pass filter can allow the band of frequencies. That bands can be calculated from this very simple AC circuits. LCR circuit is an AC circuit. So in AC circuit area, to produce oscillation, then to receive oscillation, this kind of LCR circuit can be used by fixing the quality. As I told earlier in the series resonance circuit, when the quality factor is very small, then the circuit is a wider band gap circuit. If the quality factor is a higher one, the circuit is a narrow band gap circuit. In many applications, these wider band gap and narrow band gaps are applied. So in such areas, this kind of LCR AC circuit can be used. Now we can repeat the experiment by fixing the values LCR values in different value. Here I kept the R value as 100 ohm, L value as 600 millihenry, then C value as 0.2 microfarad. You can repeat the same experiment by fixing R value as 1000 ohm, then L value as 700 millihenry, then C value as 0.3 millihenry. So automatically the resonant frequency will be shifted from the earlier resonant frequency. So the band gap also, band width also will shift. So the same components can be used to receive different type of frequencies. That is the use of this LCR circuit. Thank you.